So far, as we've talked about the properties of gases, like pressure and volume and temperature, we've focused on the gas trapped inside something, like a balloon or a syringe. But that kind of takes for granted a gas that is always around us and constantly exerting pressure at a certain temperature and volume. And that is the air around us. Our atmosphere is made of a bunch of particles, mostly nitrogen, some oxygen, some carbon dioxide, and argon in very tiny amounts, as well as a couple other trace gases. And those particles are constantly moving around us and exerting pressure, hitting on us, just boom, 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 constantly. Okay, we don't really notice it because we're used to it, but it does exert pressure, and it affects the things that we do in lab. Typically, we just kind of ignore it. We write it off as, this is 1 atmosphere of pressure. It's just what we're used to. It's constantly pushing on everything in our lab, and so we kind of leave it as that. But the power of air pressure or atmospheric pressure can actually be significant if you think of how things push back. Well, air pressure to us might not seem like much, but when there's nothing to fight back against the air pressure, can be quite a bit, and it's one of the best ways you can see just how much power can kind of come from the pressure of the particles in the air around you. So, for example, if you've ever used a suction cup, like on the end of a Nerf dart or something like that, suck something to your wall or your shower, well, that works by air pressure. A suction cup is not sticky, it's not adhesive like tape or glue, all right, but it uses air pressure to hold it in place, okay? Now, the air pressure is no greater than normal. It's not like we're cranking up the air pressure on the outside of the suction cup to all of a sudden make it stick to something, right? It's pretty much the same. I can just pull this right off, okay? But instead, we are making sure that the pressure on the other side of the air, on the underside of the cup, is less, okay? So I have a cup on the bottom of this pencil sharpener, and I've got a lever here. And if I move the lever, I can change kind of how much space there is in this little cup underneath this little divot. You can see that. Okay, so if we follow Boyle's law, if I have some air trapped underneath here, okay, and then I kind of make the cup bigger, I increase the volume, the pressure should do the opposite. My pressure should drop as long as temperature is basically staying the same. Okay, so if I place the cup on the table and I pull the lever, I increase the volume of the gas, the air, underneath the suction cup, okay, which means the pressure drops. But there isn't a whole lot of air down in there anyway, compared to the air on the outside especially. So I have all this air pushing on the cup here, and I have a little bit of air that I've now reduced the pressure of underneath the cup. So when I try and lift it up, it's really stuck on there. Okay, it's not impossible to pull off, but it's pretty darn good. Okay, we can better show this with something called Magdeburg hemispheres. Okay, this is a vacuum pump, and these are the hemispheres. They're basically just big pieces of metal, a little hefty. They can stick together, and they're greased, so they do stick a little bit. Okay, but not much. I can easily pull them apart. Okay, there's a valve on this one, which I can use to hook up to the vacuum pump. Let me set this down. Set that there. Okay, so I'm going to open the valve up. I'm going to attach this hose to it. Just like that. Then I'm going to run this vacuum pump to suck the air out of this. Now, at this point, it's just going to suck all the air here and then just move it somewhere else. It's not going to do much. So I need to close this off by using the other half, the other hemisphere. Close that off there. Again, I can pull off pretty easily right now. Okay, set that there. Gonna suck the air out. Pressure drops. I'm gonna close the valve. That way the air can't escape. Now detach the hose. There we go. All right, and now. Okay, it's a lot harder to pull apart. If you really get these greased up, it's almost impossible. You really got to tug at it. You can get one person on either side of these and just like, it's pretty cool. So those are two ways we can demonstrate air pressure, but there's a third way we can do it, and it's one way you can even do at home. Right? Get this out of the way. So I'm not bumping into it. Okay, over here, I've got some cans, and I've got a hot plate. I'm going to crank up the hot plate to about 8. Okay, but if you're doing this on like a stove top or something like that, just a high setting. Whether you got a frying pan or something you're going to set your can on, something. Just make sure you're safe about it. Don't do anything crazy. The crazy stuff will happen because of the science behind it, not because you're being irresponsible with fire or something like that. So I've just got a hot plate. I'm going to turn it on. It starts heating up. All right. Now what I'm going to need is a can like this, a soda style can, so not like a green bean can or something like that. Okay, or a coffee can. Okay, that's got a small opening on top here, and I need it empty and rinsed out. Okay, non-alcoholic is best because alcohol vapors can be flammable, and we generally don't want them anywhere near a heat source. Okay, so I've got a can. I'm going to put about 10 milliliters of water inside here. Right now it's empty. We rinse it out just to make sure that we also don't have any of that sugary stuff that will burn with the heat. It smells bad. It's just not a good time. So I'm going to get about 10 milliliters of water. If you're doing this at home, you can do a conversion for yourself with Google, but it's not that much water. It's just, a small amount like that. Pour it inside this can. So now I've got a little liquid water inside there. I'm going to set it on the hot plate. Let it heat up. Okay. Now I've already got these other cans set up, so we're going to run a couple different versions of this experiment. So I've got another 10 milliliters of water in this can. I've got about a little more than 10 milliliters of water in this can that we're going to pull off early later. And this one's got a lot of water. It's like 50 milliliters of water. It's like way too much. Okay. Now, I've got here 2 big beakers. Basically just need 2 big containers that can hold water. Ideally, we want to use ice water for this. Okay. Enough ice to make the water cold, but also we want to leave enough room for us to dunk our can. We're going to be like putting our can in like that. Okay. Now, just to show, does it really matter if we're using ice water or not? We're going to use a beaker like this, and the result's going to be actually pretty interesting if you talk to other people that have done this and see how it turns out for them. Now, again, we're going to be dunking our cans in here, so I actually probably don't want that much water. That's probably good. So we want to have room so we don't overflow the beaker or whatever container you're using. Okay. So these cans here are going to get pretty hot. I've got a pair of tongs so I can move them around without hurting myself. I'm going to move this one back a little bit. I'm going to put this one on there too to get us started. Okay. So right now, inside each of these cans, that little bit of water is heating up. Okay, so those particles of water are moving faster and faster and faster and faster and faster. Okay, until they get hot enough to go through a phase change. Okay, where we're changing from one phase of matter to another. In this case, we're going from a liquid to a gas. Okay, water is going to change from its liquid form, the way we usually know it, okay, into a gas, which you could call water vapor or steam or something like that. Okay. So our water inside the can is going to start boiling, and it's going to start releasing some steam. Okay, so the steam you'll be able to see is actually that gas turning back into a liquid. It's kind of like cooling off in these little droplets, but it's going to show us that we have water boiling inside the can. Okay, it's a lot safer to look for the steam coming out. It usually helps if you kind of get on eye level with it, rather than trying to look down in the can. It might come at you, so goggles might be a good idea for that too. But if you're doing this at home, just make sure, don't look right down into a can of potentially boiling liquid. Watch for steam coming out of it. Okay, so ideally, we're going to have all this water boiling, steaming up through the can. Okay, and again, that steam is a gas. As the temperature is increasing inside the can, okay, we have this water turning into gas, into steam, and rising up. And as the temperature is increasing, that gas is going to start increasing in volume. It's going to spread out inside the can as much as it can. And it's also going to start increasing in pressure, okay? Since it's getting hotter and hotter, those particles are moving faster and faster, which means they hit harder. So we're going to be increasing the pressure inside the can with this steam. Now, it's not all of a sudden going to burst out or something. It does have a way out. So it's not going to do anything super exciting yet. But it is good to note that our steam is increasing in volume and pressure as the temperature rises. Okay, so our steam is going to be basically trying to push anything out of the can that's in its way. Well, aside from the water that was in there, the only thing else that was in the can was air. So our steam is going to push the air out of the can as it gets hotter and hotter, increases in pressure, and is trying to fill more volume. So all that's going to be left in the can once we get a good steam built up, okay, once kind of all that water starts steaming out, we're basically just going to have steam inside the can and maybe a little bit of liquid water, okay, but no air, just steam, just water vapor, okay. I can hear a couple of these have started boiling. All right, it's not quite there. So it's real easy to get impatient with this and to just kind of go too early. So I'm going to try doing this can first, and I think it's not quite ready yet, so it might show you what happens if you try too quickly. Okay, I'm also going to show if you do this kind of a little too slow. Okay, now ideally, we want to be able to grab the can and flip it over into our ice water, and we got to do it pretty fast. Okay, so the best way to do it is kind of have your tongs upside down like this, so you can grab your can and then turn it right over into your beaker of water. Okay, if you have it like this, then you got to try and find a way to tilt your can. You might spill some hot water on someone or something. So I find this is kind of the easiest way. So if you're doing it right-handed or left-handed, kind of feel it out first to make sure you've got your beaker of water on the right side so you can just dunk it. Okay, so again, this can probably isn't ready yet. Okay, and if you're nervous about it, you might be kind of going slow like this. Okay, and then we're going to try and dunk it in. And not a whole lot happens. Not super exciting. Okay, now something is actually happening if you can see the water level here. Which, not dramatic, it's not, jump out and do something cool, but it is part of what kind of explains what's happening inside the can here. So I'm going to give it a little bit more time. Quite a bit there. Okay, I'm going to lift the can back out. Oh, and that is quite a bit of water I've gotten up in there in the can. Now, if you don't really think about it too hard, you might just say, well, we pushed the can into the water. Of course, there's going to be some water stuck in there. But now, if I go and push the can in there, it just pushes the water out of the way. Right now, I have air inside the can. Since I, took it out, I let the air get back in that I pushed out before. So if I have air inside the can now, that's going to have pressure that keeps the liquid water out of here. So I can't just force it in there. So the fact that we took water into the can, at least sucked water into this can, means something special. It means that there had to have been empty space, and there really wasn't a whole lot on the inside of the can to keep the water out. Okay, now these two are really getting there. You probably can't see the steam on the video, but maybe I can kind of steam up the outside of this beaker. Show it off. Okay, so I do have some steam coming out of there. Again, it can be a little hard to tell, but you can also usually kind of hear it a little bit. Okay, now I think these are pretty much ready to go. So our steam has been building up pressure, and it's trying to fill a bigger volume. It pushes the air out of the can, and now what we want to do is we want to dramatically cool it. All right, we want to reduce the temperature greatly. So think about what kind of phase change that would cause the steam to go through. We start with a gas. We lower its temperature a whole bunch, so the particles move slower and slower and slower, and then they get closer together. Okay, that is a phase change from gas to liquid we call condensation, or it's condensing. Well, what's going to happen if we take all that steam inside the can with all that pressure and volume and condense it back into a little tiny bit of liquid that really can't fill a lot of space, really can't exert a lot of pressure? Well, let's find out. Let's try. I'm going to do the back can because it's a little bit easier for me to reach. Okay, it's ready? That's a pretty good one. So our can has been crushed, all right, which is kind of interesting. We went from, just a regular old can, all of a sudden, it just smashed. Well, it has to do with this competition of pressure. If my steam on the inside is really the only thing that's filling the can, and all of a sudden it condenses into just a tiny amount of liquid, the rest of the space in that can is now empty. There's nothing filling it, nothing to push on the inside of the can. All the while, there is still air on the outside, still pushing, banging against the outside of this can. If there is nothing on the inside to push back against all that pressure on the outside, even if it doesn't feel like a lot to us, it's quite a big difference. So all of a sudden, we have so much more pressure on the outside of the can that just crushes the can. And this is what we're left with. Okay, there it goes. It did suck up a little bit more water there, but it's usually harder to tell if you get a can to crush well because, again, there's not a whole lot of space in there for the water to creep into. Set the can there. Okay, so we did this with ice water so we can get a very dramatic temperature change. So we can get our steam to change into a liquid, to condense, to lower the pressure inside the can very rapidly. Okay, that helps to get that good crunch. Right? But what happens if, we don't have ice water? Will it still work? Theoretically, it should, as long as the steam can still be cooled down. So let's try it. I'm going to switch these out. Now, this can kind of go either way. We'll have to see how this goes. But this is just room temperature water. Okay, 10 milliliters of water, boiled, steamed up. Push the air out of the can. Ooh, that one kind of scared me. It still worked. Okay, sure, we didn't have as dramatic of a temperature change, but we didn't really need it. As long as we could get the steam to cool back down into a liquid, this worked just fine. Okay, just kind of interesting. That's cooled down enough. Well, that sucked up quite a bit of water. Okay, again, with all that empty space on the inside of the can, with all that empty space on the inside of the can, there's nothing to kind of keep the water out. Now, why does the water get sucked up into it? Why isn't it just that we, set the can on top of the water and it's like, there's nothing to keep the water out, but all of a sudden it's drawn up and into it, I wasn't just like constantly pushing the can down into the water. So why did the water get sucked up? Well, aside from the can pushing on the water here, there's something else pushing on the water constantly, and that is air pressure. It's atmospheric pressure. It's the pressure of the gas particles constantly bang, 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 banging down onto the top of the surface of the liquid. So if I constantly have air pressure pushing down like this onto the water, well, if I turn the can over and I put it on top of that, and then I have no pressure on the inside of this can, all of a sudden, we have a place for the water to go. Air is pushing the water down, has nowhere else to go for now until I put the can on here. That has no pressure really on the inside to keep that water out. So the water gets pushed down and up into the can where it has nothing to fight back against it. Okay? Very different from the air pressure on the outside. Interesting. Okay, so this last can, we're going to put a lot of water into. A lot of times when we do this experiment, it's kind of like the immediate next thought of, okay, we did it with 10 milliliters of water. What if we just did a whole bunch? What if we did like 50 milliliters or 100 milliliters, or we just loaded it up, And the idea is a lot of water means a lot of steam, which maybe means a bigger effect. So we can test it out for ourselves. So I've got this can going. Okay, this one started with about 50 milliliters of water. I'm going to use the ice water beaker for this one. Put that over there. And I will recycle these cans later. Okay. While that's going, you might think about why we are using cans like this in the first place. So for one thing, we do want a small opening to make sure that our steam can get out, but when we turn the can over, we don't get a sudden rush of air to fill that space. Okay, we want to keep that stuff trapped in there pretty well, so we don't have air on the inside that won't condense back into a liquid and therefore can still push on the inside of the can. If you go too fast, okay, or you don't get it hot enough, you don't let it boil for long enough, sometimes the can won't crush because you've still got air on the inside of there that's pushing to kind of fight against the air on the outside, and therefore you don't get that satisfying crunch of the air pressure on the outside being so much stronger than the pressure on the inside. Okay, so if we were to do this with something else besides metal, like glass or styrofoam or plastic, how would this be different? So part of it could be about the opening. If you're using a styrofoam cup, that's got a big, wide opening. So even if you steam it really, really good, when we go to tip it over, there's a good chance a lot of air is going to flow back in there before we can tip the thing over. So that might be an issue. You can think about how those materials take on heat. You probably don't want to take something plastic or styrofoam and just put it on a heat source and see what happens. It's not going to be good. So could be something about how they stand up to heat. You could think about how they conduct heat. So, for instance, metal and glass are pretty good conductors of heat. Right? They heat up pretty well and pretty easily. So if I don't want to sit and wait here for 20 minutes for this to be ready, then I probably want something that will conduct heat well, that will get hot fast, which will get my water boiling quicker, and therefore my experiment to be done sooner. And you could also think about, what happens to the can or the container or whatever once we get this to go. Remember, the goal is to get the outside air pressure to be so much stronger than the inside that we either crunch the material or we crack it or something like that. We want to see the effect of a significant difference in pressure, where we want all this pushing to be on the outside and not much on the inside to fight back. So we also want this to be safe enough to do. If I have to, gear up and put myself behind a blast shield to try this out, that's probably not going to be the best idea. If I'm going to have something crush or break, I want to make sure it's not going to hurt me or someone else in the lab. And if we're using something like glass, I don't know about you, but I don't want glass pieces flying at me, especially if they're under the high pressure of the air around it. Okay, this can seems like it's steaming and ready to go. So again, this is one that we loaded up with too much water. Okay, and again, we want to move fast. We don't want to pour this water out everywhere, from waiting too long. Okay, so let's see. Okay, well, it did still crush, which is nice. Let it sink in there. Sometimes if you have too much water, okay, even if you steam out all the air and you turn this thing over and all the steam turns back into a liquid, you might still have enough liquid inside the can to maintain that pressure on the inside and fight back against the air pressure on the outside. So the can's not going to crush. So if you have your can darn near full of water, don't be too disappointed if it doesn't all of a sudden crush, because you still have enough pressure on the inside from that liquid. Now, if it's just a little bit of liquid, you probably have a good chance of the can crushing. Okay? In this case, we did have a lot more water, but we still had plenty of space in the can for there to be no gas when that steam condensed, and therefore a lot less pressure on the inside of the can. So we still got that crush. Maybe it wasn't as dramatic as some of the other ones, but it still worked. So adding more water can get this to work. 10 milliliters is not some magic number that I accrued out of somewhere, and it's the only way that you can get this experiment to happen. You can do this with 15 milliliters or 20 milliliters of water. You can do this with tall cans or short cans. It's really fun to test out the different parameters and see what you can mess with in the experiment and still get it to work. But you can also think about, if it doesn't work, why didn't it work? What happened? What went wrong? What was different about the experiment to get your results to be different? Okay? So hopefully this demonstrated the power of air pressure, gave you kind of some new insights on how the world acts around us, and gives you a new idea about how gases, work with pressure and volume and temperature, and just how significant that pressure can be.